Okay.
My name is Mohammed Al Batal. I'm a technologist at the CTO office of Seagate Technologies. I'm also the co-chair of the NVMe HDD subgroup within the OCP community. Today I'm proud to show you a Seagate demo for the first ever native NVMe HDD solution. What I mean by native is it's non-bridged solution with an SoC on the main PCB of this 3.5-inch form factor drive that will allow for.
So we apologize about that. So this is not working as far as the website. That was my concern before. I can show it there. Yeah, but okay.
Tri-mode transceivers with SAS, SATA, and NVMe protocols, all built into the same SoC. The same SKU will be shipping eventually from Seagate with different firmware loaded on that hardware SKU to be able to communicate with the OS at the SAS layer or SATA layer or NVMe layer. So, whatever we program it with before shipping, that's the native protocol that the drive will be of that flavor. The SoC has multiple IP blocks for each of those protocols that is capable of being enabled with that firmware load. This is specifically the NVMe IP block is a third generation hardware IP block that is also controlled by firmware for error handling, but it's mainly completely done in hardware for protocol, cracking the headers, finding out whether it's a read or write or management command. The firmware is mainly for error handling. It's leveraged from an SSD that's third generation. It's been shipping, and our plan of record is at this point is to enable key customers with not only the EDU units, the engineering demo units that are going to be available in September 2022, but also with POC 212 enclosure that we're going to go over later. We're also proud to announce also that we are providing customer demo units will be available in mid-2024, and those will also be for key customers with a wider customer availability. The demo is not specifically for the drive itself, but also the drive and in a 2U12 enclosure that will have the connections with copper connections to the host CPU, and between them there will be a redriver card that's available with a switch on it. This switch happens to be from Broadcom, but it could be a microchip switch as well. And on the 2U12 enclosure, we have what we call an IOM, an IO module. In that module that lives inside the 2U12 storage enclosure has a switch on it that basically also available from both microchip or Broadcom with interoperability with the host-based redriver switch that is shown in the demo. We are on phase 1 of our IOM development, so everything you're going to see at the demo today is PCIe Gen 3 and limited to that because of the planning that we have for phase 2 being Gen 4 capable with all the signal integrity capability there. What we've done here is we've leveraged an existing 2U12 enclosure that was used for SAS, and we've revamped the MIP plane. That's the PCB board between that connects between the IOM and the multiple 12 3.5-inch drives. And that connectivity is done today with Gen 3, and we'll go to Gen 4 on the phase 2. What we'll also do in the phase 2 stepping of this solution, we will provide a by 16 Gen 4 RNIC connectivity or to a smart NIC connectivity on that same IOM built in within that canister, and providing advancements of NVMe or fabric connectivity, because our drives will have controller memory buffer capability as a feature. That's a very critical feature for providing fabric attached at similar cost and of a BOM cost of a SAS JBOD. You know, it's very critical that we're enabling a solution with fabric attached to this storage JBOD. The NVMe protocol is also critical because of the reduction in the stack in terms of OS layers and driver layers that will be required if it wasn't NVMe. Ideally, we want to bring the most cost-efficient solution to the customer, and that's what we're aiming towards within the OCP subgroup working on this NVMe requirements. The drive features will not stop at CMB, but will extend to other NVMe 2.0 rotational media features, and the OCP team is there to selectively pick which features are the most relevant to the OCP community. And now I'll introduce you to Tim Walker to take you through the main demo, and thank you.
Thanks, Mohammed. My name is Tim Walker. I'd like to walk you through this graphical demo we have to demonstrate the NVMe hard drives. In the system today, we have 3 different types of NVMe storage. We have a production Seagate SSD, that's for sanity check. We have 2 native NVMe hard drives from the drive operations in Longmont, and we have 2 dual actuator NVMe emulated hard drives. They have an FPGA front end to emulate the NVMe target controller for us to develop the dual actuator interface from the Seagate research team in Pune. The storage is all installed in the 2U12 chassis that Mohammed was telling you about, and it's being driven by an i7 desktop that has lots of flashing LEDs, so be sure and come by and see it. We divided the screen into 12 rectangles. Each one represents one of the slots in the 2U12. We don't have drives installed in all of them. In those rectangles, you see an array of those vertical bars. Those represent the submission completion queue pairs, which we set up 1 per core. In this case, it's an 8-core i7, so there's 9 queue pairs, 1 for each core plus the admin queue. The OS is Ubuntu 21.10 desktop, and the controls on the right let us configure a basic workload to exercise the storage. So let's set up a 64K sequential read and see what happens. So now that we've kicked off the workload, you can see the activity on those vertical bars indicating the commands being distributed across the various queues as the FIO workload moves from core to core on the CPU. We're also reporting some bandwidth and IOPS numbers. The drives are really early in the development cycle, so the performance and some corner cases on the interface really aren't there yet. The dual actuator emulator drives are for interface development work, and they won't be productized in this form. But it's a really encouraging milestone to see hard drives behaving themselves on the NVMe bus. We designed the 12-drive PCIe chassis with downstream daisy chain links so that we can assemble a PCIe fabric across multiple chassis and do some early system integration work looking at larger numbers of NVMe hard drives simultaneously on the bus. I hope you enjoyed this demo, and I hope you'll stop by our booth and take a look at it in person. I'll let you drive. Thanks.
And whenever you get a chance, please send us some questions. We'll be happy to answer them after the video.
And for the virtual OCP visitors, we wish we had been able to see you face to face, but we'll be able to answer your questions as well. We're excited to be members of the OCP and present to you. Thank you.
Thanks a lot.
Thank you. Great, thank you. I think what we're going to do is open it up for questions online and see if we can get some questions answered.
All right, so if we don't have any other questions, we'll take a short break. Our next presentation starts at 3 p.m. on the dot.
Thank you.